Hello there. Today we're going to be looking at hypothesis tests for a small sample size. Okay, I apologize this got cut off, but what does that really mean? It means that our sample size is actually less than 30, which then implies we're going to be using the t-table this time to kind of come up with the critical values. Well, our first example says here, a survey of 15 larger cities in Canada finds the average commute time one way is 24.5 minutes. A researcher thinks the commuting time is actually greater than the reported figure. To help prove her claim, she takes a sample of 25 commuters and determines the average time is 26.1 minutes with a standard deviation of 5.2 minutes. At alpha equal 0.05, is she correct to think the population commute time is greater than the reported figure? So what we're trying to do here then is, you can see there's direction given, right? So we're going to come up with our null hypothesis and alternative hypothesis. And, well, since there's direction there, that means that, well, this tells us what direction the tail will be in. It's one tail, and it's greater than, it's pointing to the right. So let's find out what our hypotheses are as well as the picture. Here's the null and alternative hypotheses. And you can see this is greater than. Equality is over here with the null hypothesis. Greater than, that means it's going to be a right tail test. So the picture looks something like this. We draw our graph. Here's the tail on the right hand side, and we have our do not reject H0 and our reject H0 region, critical region, non-critical region, and we need to come up with the critical value. And what we're going to do is we're going to use the t-table with degrees of freedom 24, and since it's one tail where the alpha given in the question was 0.05, right, the tail is 0.05. When we look at our t-table, this is the way this works now. Okay, so t-distribution for hypothesis testing, that's appendix 12.4, and we first say, is it one tail or two tail? It's one tail where the alpha is 0.05, and then we go down and down that column to 24 for degrees of freedom, and you can see you've got 1.711 for the critical value. Okay, so that's where that number comes from, right there. So that's the threshold. If it's if our t-test is greater than, it ends up here. If it's less than, it ends up here. This is the value I got for t, and how did we get that? Here's the calculation. Instead of saying z is equal to this formula, we're just going to say t, that's our test value, and we put our values in. You can see that we have the collected value, the stated value, the claim, and standard deviation, and divided by the square root of the sample size. Doing the calculation, unrounded is right here, 1.5384. We're going to round to 3 decimal places because the t-table gives us information to 3 decimal places, so we can compare values. So you see that in this case, our test value ends up being right here, right? So it's in the do not reject region, and that's what we're going to state, as well as the conclusion. Okay, so let's put that together. And so here's our decision: do not reject H0, and here's our final conclusion based on the null hypothesis up here, right? So based on sample data, there's not enough evidence to prove the mean commute time is significantly greater than 24.5 minutes. There we go. Let's take a look at the next example and see where that takes us. So with this example, it says it was reported that the average rent for office space was $17.35 per square foot in the Niagara region. The real estate agent thinks that this is not correct. She decides to test the claim and selected a random sample of 15 rental offices and found the mean rent to be $18.73 per square foot, with a standard deviation of $3.74 per square foot. At alpha 0.05, was she right to question the reported figure? So in this question, you can see there's no direction stated, right? So that means it's going to be a two-tail test, right? And the hypotheses are as follows. The mean is equal to $17.35. The mean is not equal to $17.35. And like I said, that represents a two-tail test. What does the diagram look like? It looks like this. Okay, once again, t-table, we ask sample size less than 30, use the t-table, degrees of freedom equal 14, okay? And it's a two-tail test, so I'm going to draw the two tails, and once again, it's a question of knowing where do these two values come from. If we take a look at our Z table, once again, it's a situation where is it one tail or two tail? It's two tail first, right? So that's first step. And then what was the level of significance? It was 0.05 for the two tails together. And scrolling down until we get to degrees of freedom of 14, you see the value is 2.145. So that's how we got the critical values in this example. All right, so one negative, one positive. Remember that that's going to be the case. Next is to come up with the t-test, okay? And it's like the Z score, but the t score in its place. Let's see what you come up with for that. So the value I got here was 18.73 minus the mean that was stated, 17.35. Standard deviation divided by square root of sample size. Once again, I don't round until the end. This is the unrounded value. This is the value to 3 decimal places. And you can see then that it falls within the do not reject region. So since it falls in that, the conclusion is do not reject the null hypothesis, and then we'll state our final conclusion based on that information. So based on the sample data, there's not enough evidence to prove the mean rent is significantly different than $17.35 per square foot. You start to see the pattern, right? Okay, so next example, see what you come up with, and I'm just going to put the solution down and walk you through it. So this is what I got for this question. So it says a call center is looking into wait times for their staff to take a call from customers. It is speculated that the average wait time for customers to reach a service agent is 540 seconds. Management thinks the average wait time is actually less than, right? Less than. To prove this claim, a sample of 16 calls were taken, and the mean time was found to be 510 seconds with a standard deviation of 45 seconds. At alpha 0.01, is there enough evidence to support the claim that the mean wait time is less than the 540 seconds? Well, the less than gives us direction. There it is. Okay, and it tells us it's one tail. So the mean is less than 540 seconds, which is what we think. And then we also write the null hypothesis with the equal sign included, right? Opposite and equal sign. Now this tells us how to draw the diagram, and it's left tail, right? And of course, one of the things we should ask is sample size less than 30 or greater than 30. In this case, it's less than 30, which means we use a t-table. With degrees of freedom of 15, there's 16 samples taken, and 15 is degrees of freedom. So we go to our table, and we're going to find the critical value, the threshold here. And when we look at this, so 0.01 left tail, right? So 0.01, sorry, let's go back up here. One tail, 0.01, and then degrees of freedom 15 gives us this value, 2.602, right? 2.602. And that's where we came up with the value here, 2.602. But because it's on the left-hand side of the diagram, right, the mean being here, it's going to be negative. In terms of the t-test, when we put the values in, this is what we got from the sample. 510 minus the claim, 540. And it turns out that 2.667 is the value, the test value, when we round to 3 decimal places. And you can see in this example that our test actually works out to be in the rejection region, right? So we are going to reject the null hypothesis. We're going to reject this and accept this to be the case. We're rejecting that, accepting this. So let's state the conclusion, and once again, how does that look like? So based on the sample data, there's enough evidence to prove the mean response time is less than 540 seconds. And we're done. Let's take a look at the last example, and same deal. I'll ask you to read and put it together, and I'll walk you through the solution. So in this case here, Old Navy clothing store wants to launch their line of clothing for women in another country. Their current clothing sizes are based on the assumption that the average height of a woman is 162 centimeters. To determine whether they can simply ship the clothes to a new country, they select 12 women at random in the target country and determine the mean height to be 155.2 centimeters with a standard deviation of 6.2 centimeters. Based on alpha 0.01, how should they proceed to enter the new market? Should they adjust their line of clothing? All right, so this is what I come up with in this case. It's either stating that the mean is or is not, no direction is given. So that means that our two hypotheses, equal to or not equal to 162, give us a two-tail test or two-tail picture, right? So two tails, right, is drawn, and then we have our do not reject region and our critical region or rejection region being the tails. We need to go find the t-value, the critical values, and according to this, 12 women were selected at random, so we know that the degrees of freedom in this case is going to be 11. So 12 minus 1 equals 11. Okay, so let's go to the table, and two-tail test, 0.01 for alpha, and degrees of freedom 11. So, degrees of freedom 11, two-tailed test, alpha 0.01, and you can see 3.106 is the value that's going to be used in our in our picture. And that's what we got here. Right, there it is, and there it is. One being positive, one being negative. The t-test is as follows. Rounded 3.799, and you could see then that the mean, or sorry, the t-test is in the rejection region, so we will reject this. We are going to reject that the mean is 162, and we're going to state the conclusion. And here this is what I got. And based on this, based on sample data, there is enough evidence to prove the mean height is not 162 centimeters. Of course, we can also ask the question, we might think that's greater than or less than. And once again, we would state that first and then do the testing. Otherwise, you're kind of forcing your own conclusions. So we always speculate what the hypotheses are first, and then we perform the test and prove or disprove the claims. Hope this helps. I'll post the homework up on Blackboard, and good luck, guys. Have fun.